Greetings students. It's almost last class in my course, and today I will be doing a little bit about process waste handling and zero liquid discharge concept. And in the last class I had done, in the last class I had discussed about the batteries and fuel cells, and after the discussion on the electrochemical technology and electroanalytical techniques and atomic structure and other related topics, now we come to the end of the course, that is on process waste handling and zero liquid discharge concept. I have already completed, I have already talked to you about process waste handling. So, I will not talk much about process waste handling, except to say that many of the processes, process wastes are in large volumes, low concentrations, and maybe toxic and hazardous wastes, because most of the process wastes in electroplating industry and electrochemical industries are acids, alkalis, and metal ions in the effluent, and of course there will be vapors and gaseous pollutants will always be there, and then there will be solid waste. So, both liquid, solid and vapor waste effluents will be there in the electrochemical industries. I think I have completed most of this. Just for the sake of brevity, I am showing you these slides. I am not going to explain much to you during this, except until we start our discussion on ZLD. So, this is for your kind reference. Let us see how best we can do. These are the metal finishing industries, and then they are final product. What are the typical operations, and then waste origination. This is regarding major types of wastes in electroplating industries. Other industry wastes also will be almost similar. Then these are the salts, cyanides, etc. Then treatment corresponding to different types. Then specific steps we had discussed earlier. Cyanide waste treatment, there are number of possibilities. We need not be afraid of cyanide in the effluent, and chlorination, etc. These I have discussed in detail. And then sludge, electrochlorination, etc., where there is no sludge. And then typical common plating baths, bath formulas we have discussed. Then flow chart for some of the common plating baths, followed by plating waste, different kinds of industries. Then basic treatment, all these we have discussed earlier. So, I am just reminding you quickly what are the steps involved before we proceed on to the ZLD. So, batch acid neutralization, all these things we have already covered. Chrome recovery systems, vacuum evaporation, reduction, precipitation, followed by neutralization, and then I had discussed with you about the solubility products of the hydroxides of many of these copper, zinc, lead, silver, cadmium hydroxides. Their solubilities are slightly minimum, their solubilities are minimum in alkaline conditions, but solubility will increase in acidic conditions below pH 8. If you look at the solubilities of sulfides, then also there is a possibility that we can collect them of the order of about 10⁻⁻⁴, that is ppb levels. Precipitation is possible. So, these are typical reactions I had shown, and two types of complexes with sulfide precipitation, their pH effect, and then a typical procedure for treatment. Then all the processes including various wastes requirement, this we have discussed. Then some flocculating agents needed for collection and precipitation of some of the sludges, and sludge treatment I had discussed a little bit, sludge disposal followed by sludge containment, etc. That brings us to the last discussion part, zero liquid discharge. What do we have here? Here I will give you a small outline of what is zero liquid discharge, and I would like to tell you at this point that zero liquid discharge is a very, very important concept in the 21st century living. The basic thinking is, if the effluents contain toxic substances, then they have to be separated. Then if I separate, would the water be reusable or not? If I am able to separate the pollutants, would it be reusable or not, the effluents, treated effluents? The answer is usually no. It has to go through at least about 600 feet depth fall and about 20 kilometer flow before it collects enough oxygen from sun's rays and from the atmosphere and enough radiation from sun's rays to get natural purification, that too subject to proper dilution. So, basically the convention is wisdom, rather wisdom says do not use that. So, but industries we cannot stop. So, what do? We come out with a concept of zero liquid discharge. Use whatever amount of water you need, but do not discharge from the factory or industry. Then what do? You either recover and reuse or evaporate it. These are the two basic concepts of zero liquid discharge. It is being applied all over India and all over the world also. The concept is gaining strength, and I want to introduce you to these type of treatment, and it will stand in good stead for you when you go to industries. So, here is the outline: history and motivation, conventional ZLD, hybrid ZLD, emerging ZLD and near ZLD alternatives, followed by outlook. What would be the final outlook? Then here is the history. Somewhere around 1970s we started talking about it, and in America it was driven by the regulator. Tight federal regulations on salt discharge to surface waters were introduced, especially due to salinity problems in the Colorado River. So, regulations were mainly concerned with power plant discharges from cooling tower. Usually cooling towers have blowdown and scrubbers, and Clean Water Act came in 1974. First ZLDs installed were about 500 to 2000 GPM, GPM means gallons per minute, and based on evaporation and crystallization. If you evaporate, then the water vapor in the air can be carried over by the clouds, etc., and then it can be redeposited as a pure material. There is enough dilution in the atmosphere for the water vapor to get almost purified. And then regulations are expected to keep tightening again in the coming years, and new EPA guidelines are expected in 2022 now. Even in India, we have zero liquid discharge concept in almost all the states. So, what are the current drivers? The current drivers include, the major driver for using ZLD include environmental regulations for discharge of specific solutes, salts, toxic elements, nitrates, nitrites, cyanide, chlorides, hydroxides, sulfides, etc. And then water scarcity is another driving force, water stress in the growing world. And then economics, recycled water becomes more affordable as the water supply from conventional sources becomes more expensive. This is a very simple economic content. So, growing responsibility and education towards awareness of environmental issues is also one of the driving force, followed by ZLD cost that is high in most cases might become a more economic solution when waste needs to be transported in large volumes over long distance. Here I want to add that if the quantities are really large, then you cannot transport so much of liquid elsewhere. But if you go for ZLD, what remains after taking out the liquid is a very small quantity of the waste. So, that will become much cheaper in handling. So, still in spite of all these advantages, ZLD has some drawbacks also. As of now, it is very highly costed, that is both capex and opex, capital expenditure and operating expenditure is very high as of now. A custom design has to be made on case to basis instead of a general design. And then there are difficulties to deal with the complex streams. For example, petrochemical streams will have lot of problems, especially the wastes that are generated would not be common with many of the effluents that are being produced in other industries. They are all special industries where they need the sort of special treatment only. So, I can show you a little bit of the petrochemical problems. For example, petrochemical and petroleum, synthetic fuels and petrochemicals, oil refining, all these are very complex effluents. And then power, sometimes if you are using coal for power generation, again complex effluents, followed by these gravity drainage and microelectronics industries which may contain toxic elements. Then heavy oil recovery is another aspect where current and potential markets for ZLD are sort of expected to make rapid strides in progress. So, there are other industries, for example, cogeneration, pulp and paper, coal mining, fertilizer, solid waste, battery manufacturing, PVC, coal, ethanol production, all these are very important industrial aspects, followed by tertiary treatment of municipal wastewater effluents and inland desalination. So, conventional thermal ZLD technology basically is based on evaporation and crystallization operations. Evaporation usually aims around 90% water recovery, whereas crystallization may achieve even 100% recovery. We do not mean 100% when we say 100%, but at least 99.99% should be feasible. So, solids can be further dewatered on a filter press for landfill. There are couple of mistakes here. Double typing has taken place. I request you to bear with me. I have tried to correct it as much as possible. So, but does not make sense to have that kind of mistakes. So, latent heat of evaporation is partly recovered. Operational and capital costs are still very high as of in ZLD. For example, in desalination, you can see that 20 to 40 kilowatt hour per cubic meter energy consumption is there compared to 2 to 3 kilowatt hour per meter cube for desalination. So, use of chemicals and expensive corrosion materials is another aspect that is as of now a small hindrance to ZLD objective. See the complex ZLD operations, and these are all for petrochemical industries, only effluent treatment systems. So, it makes a lot of complicated engineering design, cost, treatment cost, etc., but you can see that the wastage or effluent in the gaseous form coming out is very less here. Then there are other techniques, for example, this MVC evaporation technique. So, here suspended solids are removed prior, and the calcium hydroxide and magnesium hydroxide precipitations are commonly employed. And here I have a boiling point, a fraction evaporated, etc. Some of these things, if you study well, you will be able to know. I am know about it, and I am not going into detailed aspects because these are all very simple flow sheets. And anyway, whenever you want to design a ZLD, you will have to do it case by case only. So, I am not going into detail. These are the common typically available systems. So, for example, if you go for crystallization, it is not very tricky. For example, here I have brine and steam is there, condensate is there. We add a little bit of antifoam sodium hydroxide neutralization and take it to crystallization, and then after crystallization filtration and collection and disposal. Similarly, vacuum crystallization is also another system. Here the temperature for boiling will be reduced quite a lot, followed by higher salt concentration is a very typical advantage. Now, hybrid ZL technologies are there, a little bit mixing of the technologies, but there is strong motivation to employ energy saving processes. For example, this multiple evaporator system, MVC crystallization, etc. Some of these technologies share compare with cost of desalination, they are comparable. For example, RO is much cheaper than ED, that is much cheaper than thermal evaporation, and ED is electrodialysis. So, reverse osmosis is one part. What does it do? Reverse osmosis rejects the salt, passes water, energy requirement is approximately 2 to 4 kilowatt hour per cubic meter. Then nanofiltration used to remove the salts, not suspended salts, not dissolved salts. Electrodialysis removes ions, costs are intermediate to RO and MVC. Natural evaporation again slow and large footprints, again not so favored, but any of these reverse osmosis, nanofiltration, electrolysis, electrodialysis and electrode reversal. All these things are quite often employed in modern day zero liquid discharge systems. So, another possible motivation is the presence of organics, volatiles, etc., colloids, etc. Here what happens is many of the volatiles will not be economically recoverable if the concentration is very low. So, we go for evaporation, and then if we cannot recover, if we cannot let them into the environment as vapors, we can go for bioremediation. Bioremediation and then this membrane units, ultrafiltration, pre-treatment, membrane biological systems. These are all very typical technologies which are well established. Then ZLD combined with RO is again a very attractive system. RO is presently the best and most energy saving available technology for desalting. The purpose is then to use RO to recover as much water as possible before MVC. If you wish to recover reverse osmosis water, average efficiency is approximately about 50%, but nowadays the recovery varies from 85 to 95%, and the TDS, total dissolved solids, osmotic pressure becomes too high for more than around 80,000 ppm or something. So, scaling may be elevated to some degree by anti-scalants. And then fouling of course is always there. So, if there are organic substances, colloids, biofilms, etc., you cannot employ RO systems. If it is purely aqueous system, then RO system would work very fine. Then this is the RO system. Here I have an RO system, RO product is there, RO concentrate is there, and this is a brine concentrator. This can be concentrated and crystallized, remove the solids, and again whatever comes out can be mixed with RO product. This is condensation product here. So, cost of brine concentration for this is approximately comparable, a little less, and this is suspended solids concentration. This is 50, this is 100, this is 150. The lesser and lesser suspended solids, the cost will increase more. So, RO limitations are there, as I had already told you, that if you want to recover more, then the cost will increase exponentially here. You can see this now, and same thing is true with brine also. Suppose you have a salt effluent, and then you want to recover better 90% or something, you can see that brine concentration also will increase in the reject, and the cost also will become very high. I am not going into details of these equations, they are all very standard osmotic pressure and normal pressure difference, etc. They relate to the efficiency. If you wish to know more about it, we will have another course on RO systems separately. Then increasing RO recovery, we can go for two stage RO and nanofiltration. Here interstage softening or precipitation also is quite common, and we advise people to go for this interstage softening and precipitation. Of course, it requires more chemicals to be used, but the quality of water, here I have given you a simple system, that is 3000 milligram per liter. Primary separation will give you 80% straight away, and remaining reject will be around 19,440, and again if you can take it to a crystallization what comes out would be the mother liquor from this would be having about 18,100, followed by another RO system where recovery would be 67% and the reject would be 54,000 milligram per liter. This can be evaporated and take out the salts, and you can either bury the salts and do whatever is necessary to store or dispose of in a standard TSDF, that is toxic substances disposal facility. Then we have RO, if high efficiency RO processes are there, they can we can remove the calcium and carbonate hardness. RO can run around pH 10.5 also, and high pH creates a cleaning environment, that is low fouling. And then silica solubility is very high, and then hardness can be removed. Salt rejection and flux are increasing, and recovery will be more than 90%. However, cost will be proportionately higher, obviously approximately by about $0.13 per cubic meter. And ZLD combined with ED, electrodialysis. Here the advantage is it need not be connected automatically. We can, it is a choice. So, ED is not limited by osmotic pressure, therefore, it can achieve much better recovery. That means, it can be used to remove the ions, dissolved salts. So, typically ED desalting cost is higher than RO, but lower than crystallization. So, that is one of the advantage, and increasing then the question arises, why not increase the ED itself, electrodialysis, instead of RO. The point is, in RO, if the quantity is very large, electrodialysis becomes very costly. So, first we go for RO, then followed by ED, so that we handle smaller quantities, but higher concentration of the dissolved salts. So, we can go for off stack precipitation or EDM in place of regular ED. And then these are the typical systems, RO followed by EDM followed by crystallizer. And onset of precipitation, this is a typical study people have done for gypsum oversaturation. This is for a fertilizer industry. You can see that onset of precipitation happens even within 2 hours of putting it in the crystallizer. That is interesting, because the salt concentration should be very high whenever you want to remove it by crystallization. It has to reach the super saturation level before it can start precipitation. So, the ED metathesis, for example, formation of sparingly soluble salts can be prevented very easily using 4 compartment units. Here you can see in the next slide. First one is RO concentrate. Here I have calcium, magnesium, sodium, chloride, sulphate, etc. These are the concentrations. If I go to EDM, take the reject of this, I end up with about these numbers, that is 322, magnesium will become 417 ppm, sodium will become 4200, chloride, etc. They all become lower than RO. That means water will be more purer in EDM, and that is the EDM feed. And what happens to EDM concentrate? So, after EDM I get 34 ppm of calcium from 322. That is fantastic, isn't it? And then salt concentration will increase quite a lot, chloride, etc. These are the rejects now. So, here you can see that EDM is much more efficient than RO alone. So, RO with EDM makes much more sense. So, this here is a presentation with RO plus EDM plus off stack precipitation, and it is a fairly simple system. Here end product is potable water, straight away you can take it for drinking, and the reject goes to calcium sulphate feed water and purge it and then add sodium. So, from the EDM concentrate we can take it there, filter and reuse the material. So, these are all different systems for precipitation. For example, in this chiller sodium sulphate can be very easily removed just by cooling the system. So, sodium chloride recovery can be done by adding magnesium chloride. So, like that there are different chemical systems available. All the rejects can be added to final calcium sulphate feed water system where it is purged, and then this can be taken back to RO for treatment. So, ZLD becomes really effective, especially when you have different kinds of waste having a variety of salts. Then there are biological systems, couple of them, and then these things remove TOC, total organics, as CO2 and sludge. They may leave some recalcitrant organics, but it will not be much, and there are methods to remove the such organics, and MBR-UF is significantly more expensive definitely, because MBR itself is very costly, membrane biological recovery. So, pensive but offers a smaller footprint, and but this MBR can be as it can be very less space consuming. So, that is one advantage we have here. So, MBR followed by 2-stage RO, evaporator and treated water, we get the clear water that can be taken to different systems. Here it is a tannery waste system. Then emerging and state of the art ZLD solutions I want to discuss. Not much to add in this. Here several alternative technologies, Sparrow, Arrow, and here it is pH elevation precipitation followed by RO, and then VSEP. These are RO systems. In such systems, RO membranes are kept shaking continuously, so that there is no build-up of the fouling. So, this is a very fantastic technology which I had the opportunity to review it recently. Very nice, 85 to 95% recovery straight away only from RO systems. And then we have this HEPPM, that is ED treats the feed to RO. Then forward osmosis, again instead of reverse or normal osmosis also can be employed, followed by molecular distillation and wind assisted intensified evaporation, etc., wave it is called. These are the alternate technologies we normally explore depending upon the volume and cost. So, for example, in Sparrow process we have hard water from mining industry. All you got to do is feed it, and then here is the calcium sulphate precipitates and seed crystals, and then not on the membrane surface, but outside, but the permeate what you get is very simple reusable water. Here it is other systems I have discussed, described here just by notation regarding the actual system. And then forward osmosis, very useful today in oil industry, and it was proposed as an alternative to RO. It is viable only when waste energy is available. This is a forward osmosis figure, I will not go into details, except you can study this yourself and come to some sort of understanding of the process, because I have put most of the titles here, most of the components, and you can imagine what all they do, each component that would be there. And then enhanced natural evaporation is again another process which was used earlier in about 20-30 years before. People used to have evaporation ponds, and these are widely used as part of ZLD, but their footprint can be excessively large, because most of the time what people do is they maintain large ponds where the water will evaporate naturally, leaving the concentrate, and the concentrate will have different layers in the pond, where anaerobic and aerobic processes are in equilibrium with each other. So, normally for very complex waste, such ponds will become very useful. So, wave may offer 1/15th of the land and 1/3 of the capex expenditure for the same evaporation rate. So, this is something like a typical plant, and here is the first one is the RO, RO1, RO2 followed by brine treatment wave. It makes a lot of sense, whereas here it is only RO1 and RO2. So, outlook, industry outlook is something like this, that efforts to continue to find the alternatives to energy intensive evaporator hybrid systems are there. With increased recovery will be the dominant approach. Progress is being made in lowering the cost, and industry analysts predict a cumulative annual growth rate of more than 200% in the next decade. I think it will be well for us to know more about these things as and when the opportunities rises. And I would like to conclude my discussion about the RO and ZLD systems, and I would like to say thank you for being with me in all these 41 lectures, and I hope you had good opportunity to learn many things which I myself did not have the opportunity when I was a student. But if you need any help from me, you would know how to contact me, and I will be very happy to have you with me whenever you are in difficulty. Even otherwise, you will all be, you are all my students now, you will be my good friends later. Thank you very much. Have a good career. Thank you very much.